Hi everyone, welcome to my channel. My name is Fikrat. This video continues video series dedicated to learning Microsoft Fabric. In the last few videos, we have been looking into different aspects of creating warehouse solution. So we have explored different data modeling topics, including creating primary keys, foreign keys. We also learned different programming and orchestration components of warehouse. Today we're going to use all this knowledge to build end-to-end sample warehousing solutions that will follow a Kimball dimension modeling methodology. So this is going to be a very interesting and a fun project, and I'm excited to take you there. Let's get started. Here are the topics that I'm going to cover today. So we'll start with the solution architecture discussion, where I'll explain how we are going to ingest the data, what data zones to expect. Then we'll move on to discuss data architecture. So I'll show how our data schema will evolve as it moves through different data zones. Next, I'm going to walk you through the code that will take care of data modeling part. So basically creating tables and the keys and the relationship between them. Then we'll move on to another part of the demo where I'll share the sample code that can be used to ingest data from data lake storage into warehouse. Then we'll move on to data engineering challenges section. So here we will explore a number of different engineering challenges, and for each of these challenges I'll explain the potential solution as well as share the code implementation for that. So the first topic that we're going to discuss will be how to generate globally unique ID keys. When I say globally unique, I mean that the unique keys that are global on each table's level. So I will be using a watermarking logic alongside with row numbering window function. Next, we're going to explore how merge into logic can be handled. So for many tables, including dimension tables, you need to have upsert logic in place. So in other words, you need to be able to update and insert into your target tables. In traditional databases, you would use merge into logic. However, in Synapse Warehouse, this command is not available. So I'll explain how this challenge can be overcome. So when you are talking about dimensional modeling by Kimball, it's important to consider dimension tables that will contain change history. So that's called slowly changing dimensions, or SCD. So we'll look into logic that allows you to generate and maintain SCD type 2 metadata columns. Next, we're going to explore date-time dimension generation. So in a typical warehouse, you would have a date-time dimension that will contain different timing components that could be useful from reporting perspective. Then we'll move on to explore fact dimension links topic, where I'll explain how to correctly build relationship between facts and type 2 SGD dimensions. I'll also explain how late arriving dimensions problem can be solved. So for those who are not familiar with the terminology, late arriving dimensions are the dimension keys that may be missing from your fact tables. But when you are building your warehouse solution, you need to account for this. Next, we're going to discuss incremental factor loads techniques, and we'll wrap up our discussion with the orchestration of end-to-end pipeline, where I'll walk you through the design as well as practical implementation of pipeline that can call all these tasks in certain order. A quick reminder before we continue: if you are new to the channel, please take a moment and subscribe, as well as hit notify button so that you could always get my latest videos in a timely fashion. Thank you. Let's get started. So let's discuss solution architecture questions. In introduction video for Synapse Warehouse, I mentioned that there are a number of sources from which you can ingest your data into Synapse Warehouse. So that includes different databases as well as data lake storage. And you can use a number of tools for them. Among them, there are some code first as well as code-less tools. For the purpose of this demo, I'm going to use copy int command. That's just another T-SQL command to ingest your data directly from data lake storage. There are a number of options in terms of how you can organize your data within Microsoft Fabric. So in the introduction video, I mentioned that you can ingest data into Lakehouse using Spark workloads, and then this data can be consumed into Warehouse for dimensional modeling and consumption purposes. But you can also build your entire solution on Synapse Warehouse. So this is the option that we're going to explore here. We're going to build 3 data maturity zones. So bronze layer, which will contain raw data, so that will replicate your data's original structure. Then we'll apply certain transformations, schema normalization, data enrichment, and write data into silver zone. Then we will apply dimensional modeling to push this data into gold zone. These 3 zones, also called a medallion architecture. Typically, this architecture is discussed in the context of lake houses, but Synapse Warehouse is also based on Lakehouse, so I think that the same concept can be applied for Synapse Warehouse as well. Another thing worth to discuss here is that when you are bringing data to Synapse, you have an option to create multiple warehouses there. So you can have dedicated warehouse for each data zone. But in this demo, I'm going to use a single warehouse, and I will use different schemas for each data zone just to keep things simple. Now let's discuss data architecture aspects of this solution. So my source data will have the structure like this, where I have flat file with the mix of fact as well as dimension columns. And I will ingest this data into bronze layer, and then we'll normalize the schema. So I have covered schema normalization concept in the previous video. By normalizing, we'll ensure that we split all the related columns into dedicated tables. So in this example, we'll move all the geography related columns to its own table. Then we'll apply some other data enrichment and cleansing transformations as well, like deduplication, as well as handling null values or empty values. Finally, we'll move our data to gold zone, where we'll have dimensional model by Kimball. So we will generate date time dimension, and we'll generate type 2 SGD dimension for geography data. This kind of dimensions require extra metadata columns like surrogate keys, as well as raw lifespan columns like effective from, effective to dates. For the purpose of this demo, I have prepared CSV file, which I extracted from Synapse Warehouse, which is a sample database in Fabric. As you can see, it contains a mix of fact and dimension columns. So we have dimension columns like zip code, city, and trip date. If you want to repeat this experiment, please upload it into your blob storage and make sure that you take file path as well as SAS token. So I have explained these steps in details in the introduction video. So please take a look if you don't know how to do that. And once uploaded, then we will use a copy into command to ingest this file from blob storage. So let me navigate to SQL Management Studio. I connected the SQL Management Studio to empty warehouse that we created earlier, and I have script which contains all the commands needed for this demo. So I'll be sharing this script in the description of this video. Let me walk you through commands within this script. So my first three commands between lines 2 and 6 create different schemas so that we could organize our tables in different maturity zones. Below that, I have create table statement for sample trip data, and the structure mirrors the source file structure. If I scroll down, I have geography creation table, and this table is created within silver zone. Next, I am adding primary key to geography table based on geography ID column. If I scroll down, my next command creates trips table within silver schema. It contains only trips related columns plus a trip date column, which I will be separating a little later. And my next command adds foreign key from trips table pointing to geography table. My next command creates watermarks table to store last ID for each table. There will be only one row for each table here. I already created this table, so let me navigate to Fabric portal and take a look at the model. So here I opened my warehouse and I navigated to the model tab. By default, you will see all tables tab, which will contain all of your tables, but you can easily create new layout here, which I did. So I created new layout for silver and gold. So if I navigate to silver, I included these two tables, the trips and the geography. And as you can see, we have primary key, foreign key relationship between these two tables. Next few commands in my script contain table creation statements for gold tables. So here I need geography table, so I named it dim geography, and it's created within gold schema. So the structure of this table mirrors the structure of geography table from silver, with few exceptions. So first of all, I am adding geography key here, which will serve as a surrogate key. And then we have effective from, effective to dates columns, which indicates the lifespan of each row. And finally, I have is active column, which indicates whether or not this version of the dimension is active. So this table is designed to handle type 2 slowly changing dimensions, which I'll be describing when we move on to dimensional table transformations. My next command between lines 75 and 78 adds primary key to dim geography table. Notice that I have selected surrogate key as my primary key. So my next command creates date dimension. Here I have date key, which serves as surrogate key, as well as some additional columns like date, year, month, and the day, which will be generating from the source data. And my next command adds primary key to this table. Finally, my next command creates fact trips table. Notice that I have foreign keys pointing to surrogate keys to other tables. So my next command adds foreign keys pointing to geography table, and the next command creates a foreign key pointing to dim date table. So warehouse pipeline is usually multi-step process, and I created a separate store procedure for each step. Let me show you my first store procedure. This store procedure ingests data to sample trip data within bronze from blob storage using copy into syntax. I assume you're familiar with copy into syntax. If not, please take a look at the introduction video. To repeat this experiment, you'll need to copy your blob storage connection string in line 125 and generate SAS token and place it here. If we take a look at the next lines, we have included optional clauses to handle errors or irregularities in your files. So line 129 specifies which folder within blob storage error files will be written to. And line 130 includes credential. So here you'll need to paste SAS token for that particular folder, and that token needs to have write permissions. Another thing to notice that I included first row option here to indicate that my data start from line 2, because line 1 contains column headers. My next command is optional. It's to test the stored procedure. So I'll be using data pipeline to orchestrate entire pipeline. But to do quick tests, you can use execute command like this. And let me show you resulting data set. Alright, so let's see how we can generate unique ID keys. When you are creating dimension tables, you have to dedicate ID columns. For example, in a silver zone, you will have natural keys or business keys. So how we can generate unique keys that will be global on each table's level? When you are reading from flat files, in many cases, your file does not represent entire data sets that you can expect in your target table. So that means that you have to store your last generated ID in some watermarking table and then consume this ID in combination with newly generated IDs from your source data to form unique values for that specific table. So one way to solve that is to follow a three-step process where you first read latest stored ID from watermarking table. Then we can use row numbering function, which is a window function in T-SQL, to assign unique numbers for the data coming from the source, and then combine these two values to get table level global values. Lastly, you have to calculate a new maximum ID from your destination table and update your watermarking table. So let's talk about how we can handle merge into logic. Many of you who come from database background are familiar with merge into logic, which allows you to identify match and as well as unmatch between source and the destination tables, and apply a single operation to update matching rows as well as insert or delete not matching rows. Unfortunately, this command is not available in Synapse Warehouse. So to overcome this problem, we can use few-step process where we use inner join between source and the destination to identify rows that already present in your target table. Then we can select subset of rows which have actually changed by applying hashing function between source and the destination, and then based on mismatch between these hashing values, you can decide which rows needs to be updated in the destination table. So that will take care of update portion of the merge into logic. Then we can use left join to identify source rows that are missing from the target table and append them to the target table. I should mention here that depending on your source data, you may also want to take care of delete from the source. But when you are dealing with partial data, like in my demo case, I think this scenario is not relevant. All right, now that we have brought data to bronze zone, so let's talk about transformations in the silver zone. So if I scroll down, my next command creates a table valued functions to receive last ID for specified table. So this is necessary in order to get globally unique IDs for each table. So let me run this user-defined function. So for geography table, the last remembered ID is this value. So I already run all my stored procedure, and that's why we have some values here. But when you run it for the first time, it will return no data because watermarks table will be empty. Now let's talk about actual transformations happening within silver zone. So my next command creates stored procedure to split geography table. So here I am taking my first step to normalize my data. Within the stored procedure, I have multi-step process to handle merge into logic. So my first step identifies matching rows between source and the target geography table. To do that, I am using common table expression between lines 160 and 163. And within that, I read from source table. I use distinct command to deduplicate. And then I use coalesce function to replace empty values or null values with whatever string I want. In this case, I am replacing with missing key values. Next, in line 162, I use cast function to do data type conversions. So this column in the source, I have identified as varchar 300. Here I am converting to varchar 100. So this is just example. In some cases, you may want to convert from a string to numeric, date, and so on and so forth. Next few lines of this same command includes update command, which uses the common table expression and overrides the destination table. All right, now that we have taken care of matching rows in the destination, let's take a look at the second step, which adds missing rows from destination. So here I am using similar technique with common table expression. What's different here is that I join source table against my destination table using left join to identify which rows are missing from destination. Notice that I have filters for a null condition from destination table. All right, now that I have described the transformations within common table expression, so lines between 175 and 179 uses this common table expression to insert rows into destination table. Notice that besides this common table expression, I use user-defined function to bring last remembered ID for geography table, and I use cross-apply condition to tie this together. And the result from this function is used in line 176, where I summarize row number from source with the last remembered ID. Finally, in step 3, I refresh watermarks table by reading maximum value for geography ID from target geography table. So to recap, within this stored procedure, I I achieve multiple goals. So first of all, I normalize my source data. Then I replace null values with something that makes sense. Then I do data type conversions. I handle merge into logic in 2 steps. And finally, I refresh watermarks table with the latest ID from my dimension table. All right, now that we have normalized our dimension table, it's time to take care of fact data. So my next store procedure between lines 192 and 204, normalize trips data. For the most fact tables, you would use delete and insert approach. You'll need to come up with the right conditions to remove from your destination table. Here I am using trip date as a filtering, and it's filtered based on trip date parameter. And then I have insert into command, which reads from source table only trip related columns, but it also joins against silver geography table in order to bring geography ID columns. Notice that I use coalesce function here to replace any missing keys with -1 key. Another thing to notice that I use cast function to do date type conversion. So let's talk about HGD type 2 dimension tables handling. This type of tables require extra row versions. So basically, whenever you receive new changed version of the row, you need to add a new version and expire the old version. But you also have to add extra metadata columns that needs to be updated accordingly. So here is how we can build the logic for that. So we can first use inner join to identify match between source and the destination rows. And then from this data set, we can select the rows that have been changed using hashing algorithms that I have described earlier, and then append them to the target table. How do we assign HGD metadata columns? So for surrogate case, we can generate unique values as I explained earlier. Then for effective from date column, we can use built-in T-SQL functions to calculate processing date time. And then we will set effective to date column to some distant future date. So I have provided a sample value here. Finally, we will mark all these rows as active. As a next step, we're going to expire rows from source that have matches in the destination table. And to do that, we're going to apply inner join again and use matching logic using hashing algorithm, just like we explained earlier. However, for these rows in the destination, we will set the effective 2 days to processing date time. So basically, at that point, the lifespan will end. And then we will set is active flag to 0. Finally, we're going to use left join between source and the destination to identify rows that are missing from the target table, and we'll append them to the target table. And we will assign the metadata columns as follows. So we will generate surrogate keys using unique value generation logics that I have explained earlier. Then the effective from date will be assigned processing date time. And we'll set the effective to dates to distant future time. Finally, we'll mark these row versions as active. So I know this may sound like lots of information and could be hard to understand when presented in theoretical way, but hopefully it will be easy to understand when I explain on the demo code. All right, now that we have discussed silver layer transformations, let's move on to the gold layer where you would expect most interesting transformations. This is a stored procedure I created to demonstrate how type 2 dimension tables can be updated. So at the beginning of is 3 steps process. So first I identify rows that have a match between source and the destination using inner join. Notice that I am using natural keys to make a comparison. And then these rows are appended to destination table as active rows. Another thing to notice that I also have additional filtering to identify the rows that have actually changed. So I use hash bytes for that. So basically I apply hash bytes to the source as well as destination, and the only rows that have actually changed become legitimate target for me. Another thing to notice that when joining to target rows, I only join it against active rows. So few words about the transformations that's happening within this join. I calculate a geographic key using unique value generation methods that I described earlier. And then here I am calculating effective from and the effective to dates. So as you can see, effective from days becomes current date time, and the effective to date is time in a distant future. And these rows are marked as active. Now, because we have appended new rows to the destination table, we'll need to calculate the last ID and update our watermarking table. So that's what the commands between 242 and 245 does. So I check if there is a row matching for this particular table exists in watermarking table, and delete that, and then insert the new value that is calculated from dim geography table. So this is a step that needs to be done after each addition to the destination table, so that to keep watermarking table up to date. So my next step is to expire matching rows. Like previous step, I am using inner join to identify matches for active rows, and then set effective to dates for these rows to current processing date time. And then I mark these rows as inactive. So my next steps identifies mismatch between source and destination. So I'm using left join in this case. And then I take source values for these rows to append them to target table. Like with the previous step, I generate unique values in combination with reading from watermarking table. And here I refresh my watermarking table again. The last few commands at the end of this stored procedure takes care of maintain unknown member inside dim geography table. So as I mentioned earlier, each type 2 dimension table should have unknown member. And here I am checking if this row already exists in the target table, and if not, I insert fixed values inside this table. So that concludes the logic for the stored procedure. I have included a test command to test the stored procedure, and you can use next few commands to see how this update logic works. So if I run this command and run the stored procedure again, I should be able to see multiple versions of the same dimension. So let me run this. So as you can see, now we have 2 versions, one with old value for city and one with new value. And here the first row is the one that I have expired. So you can see that we have marked this as inactive, and its lifespan also ended at some point in past. And then from that moment, a new version of row has become active. So let's talk about date-time dimension generation techniques. Date-time dimensions are usually easier to handle because in most cases they need to be type 1 dimensions that do not require extra column as well as extra row versions. Having said that, there are some specifics for this dimension generation as well. So obviously you will need to have a unique surrogate keys for these tables. In a typical scenario, you will create big integer value from different date time components. And you can get these date time components using built-in T-SQL functions. Update logic for date time dimension will be very simple. You can use delete statement to identify which rows have already been inserted so that to avoid duplication, and then insert newly generated date dimension into the target table. And then date time dimensions typically contain different components of the date time, like quarter, months, in some cases hour. So these components can be calculated using built-in T-SQL functions as well. Okay, so my next stored procedure handles date dimensions. So handling date dimensions are much easier. So what I've got here is a common table expression that calculates different attributes of the date, like year, month, using built-in functions. I also generate date key here, which is going to be numeric value, using this kind of expression, which basically takes day, month, and the year component of the date and concatenates them together. And then I use this common table expression to insert into dim date tables rows that are not already present there. So to identify if certain date dimensions are in destination or not, I use left join, and I check for target date key column for null condition. So this is a similar technique that we have discussed in the previous stored procedure. Like with dim geography table, my next command also checks for unknown member within dim date table, and if it's not there, it inserts into this table. So let me show you sample data from this stored procedure. So as you can see, my first row is unknown member, and then I have date key, which is again concatenations of year, month, and day components. And then I have year, month, day attributes. You can also add months as a string column here, which is probably more common approach. And you can use date part built-in function from T-SQL. Another interesting topic when you are building dimensional model is to how to link your facts and dimensional tables in your dimensional model. So depending of type of dimensions, your linking strategy may differ. So building links between facts and type 1 SGD dimensions is straightforward because these tables only contain one key, which you call natural keys. So building relationship between facts and type 2 SGD dimensions is not that obvious. That's because these tables usually have two types of keys. So that's a surrogate keys as well as natural keys. So which keys is best? It's recommended practice to use surrogate keys to link facts and dimensions because of various reasons. So one reason is that surrogate key is unique within dimension tables. So if you're using surrogate keys, you are ensuring that you have many to one relationship between facts and dimension table. Another reason is by using surrogate keys, you ensure that you are linking facts to the version of dimensions that were relevant at that particular moment when these rows have been processed. So in this example, I have geographic key as surrogate key, and geography ID is my natural key. And I am using geographic key to link these two tables. Another important consideration when you are building dimensional model is to take care of missing keys. This is also called late arriving dimension. So let's say you are processing your fact tables, and for some reason you have mismatch between your fact rows and the dimension rows. So this mismatch can be because of different reasons. Sometimes some of the key values are simply empty, so you have no ways of matching to dimension. Sometimes they may contain keys that did not arrive to dimension table yet. This could be either because of human error, application defects. In any case, your application should be ready to handle this scenario. And to address this, you can add a dedicated row to your dimension table called unknown member. And then whenever you find a mismatch between facts and the dimensions, you can assign that row's ID to your fact rows. So this is how your dimension table will look like. So in this case, the first row in my dimension table has geography ID and geography keys assigned to -1. And then I have set different string values to the value of unknown. By treating your mismatches from fact tables this way, you will ensure that these rows can easily be identified by your reporting, but you can also come back and reprocess these rows when these dimensions values become available at a later point. That's why this kind of dimensions are also called late arriving dimensions. Another aspect of handling fact data in dimensional zone is update logic. So fact tables can be different types. In some cases, you have facts that are never updated. Examples of this could be transactional facts, where every day you receive new batch of transactions, which are not expected to be updated the next day. Handling this kind of facts are easier, so all you need is to identify which rows that are already present in target and delete them. In cases where your facts are updatable by nature, for example, if you're having rows that represent account balances, you can use merge into logic that we have discussed earlier. For the purpose of this demo, I'm going to use a simple delete and insert method. Another consideration when you're building fact transformation is to make sure that they are incremental, because fact tables are expected to be large. So in many cases, it makes sense to come up with parameters for your transformations that will represent some delta logic. So that could be date logic or month logic. So basically, you can pass certain period information to your transformations, and then you can use this period to update your rows in the target table. So let me walk you through the procedure I created to handle fact updates. To make it incremental, I have trip date parameter here. So this store procedure has two steps. At first, I delete the rows from target table that match certain period, and I use here inner join to dim date because fact trips table do not have date call. In my next step, I insert rows from source table that match the same period, and I join this table against two dimensions tables that I have to bring surrogate keys from these tables. Notice that for geography table, I am joining using natural key, and then I bring geography key column from this table. Another thing to notice here is that I have coalesce function, which checks if the value produced by this expression is empty or null. And if yes, I assign -1 here to address late arriving dimension problem. And then I have similar logic to bring keys from dim date table. So my next command allows you to test this store procedure for some given date. Now that we have completed coding part from warehouse side, Let's build a data pipeline that can tie these components together and run them in certain sequence. Orchestrating ETL pipelines for warehouse is another important topic. So you need to make sure that your transformations run in a correct order. So this is a sample design that I will be using for my demo. So here we have ingestion into bronze step that comes first. And then we have next two steps that are happening in silver zone. So we'll normalize the geography table and the trips table. So in my case, these two steps can be run in parallel. So I don't expect any dependency between them. And then you have to include transformation within your gold zone. So it's important that you first upload your dimensions because fact tables needs dimension surrogate keys. So we have strong dependency between them. For that reason, I have included dimension transformations first. And these dimension transformations are dependent on the predecessor's transformation. In this case, it's geography. So I'm going to navigate to Fabric. And from here, I already created new data pipeline. So I selected data factory, created new data pipeline. I'm gonna add stored procedure here. So my first stored procedure will bring the data to bronze. I'll call it ingest into bronze. And we'll switch to settings, select my warehouse connection, and we'll select bronze stored procedure. Next, I'm going to add another stored procedure to normalize geography table. So I'll select corresponding stored procedure. Then I'm going to create another stored procedure to normalize trips data. So I will select normalize trip stored procedure. I know that this stored procedure has a parameter, so I'm going to use import button to bring that parameter. And then I'll provide a sample value for trip date. So I'm going to say 2012, 13, 0101. Now that we have included a two stored procedure for silver layer, let's create dependency between bronze and the silver layer transformation. So I'm going to build success dependency between bronze ingestion and this two stored procedure. That would mean that this stored procedure will run in parallel as soon as my bronze ingestion completes. Now let's add stored procedure for gold layer. So I'm going to add another stored procedure here, and I'll select my stored procedure. I'll copy this stored procedure. By the way, if you are creating multiple activities with similar configurations, then sometimes it's easier to just copy paste. So I'm going to copy this activity and paste it here, and we'll repurpose it for date dimension. So I'll say date, and we'll select dim date stored procedure. Now, in terms of dependency, I know that data for dim geography tables comes from geography silver table. I'm going to create success dependency between these two. And I know that dim date data comes from trips table in silver. So I'm going to create another success dependency here. As a last step, I'm going to add stored procedure for fact updates. And to do that, I'm going to select one of these activities and clone it. So that's another technique if you want to repeat the same configuration. So I'll call it fact trip store procedure. Now, in terms of dependencies, I'm gonna put dependency between these two activities and the fact trips. So this would mean that if any of these activities fails, then fact trips transformation will not run. Okay, my pipeline design is complete. I'm gonna save this pipeline and execute it. So that concludes today's discussion. To recap, we have gone through a few important stages of warehouse building. So we have explored data modeling, transformations, and automations for Synapse Warehouse. The ideas that I presented here are not new. In fact, Kimball methodology have been around for several decades, and I am sure that many thousand warehouses have been created based on that. I just shared some ideas on how these concepts can be applied to solve some of the Synapse Warehouse challenges. I hope this discussion was helpful for you. Thanks for watching, and I'll see you in future videos.